Whoa. Okay, 5.3. Interpreting and sketching graphs. You guys with me? Okay, you got your notes out? Yeah. We got the notes out? Good. Put your 5.2 homework away, please. 5.3. All right, interpreting and sketching graphs. Okay. Now, this is something you've been doing for years, I think. Looking at a graph, interpreting what's happening during the graph. This is very, very important for math and for science, for gleaning information, that is getting information from a graph that you see. Also, for communicating information for data that you've collected. It's often the best way to do it. Instead of writing a novel, explaining what you did and listing all the things that you measured, if you put it on a graph where everything is in one spot, people can just look at one thing and they can kind of like trace it around. Okay, there's a point. That's okay. Look at the pattern. You can also see a pattern emerge, right? But if you're reading a 2-page document with listing all of the stuff you've measured, sometimes it's hard to see a pattern. What you do, if you do see a pattern, is you kind of like keep track of what you're reading in your mind, and you visualize it in your mind anyways. So let's just put it on a piece of paper so we can see. So this is an example of a graph, obviously. Some important aspects of the graph are the axes, right? This is axis number 1. This is like the horizontal axis. And as you guys have already told me, this is the independent variable goes on the horizontal axis. So if it's time that's passing, that's a common independent variable. Something that you're measuring is the dependent variable, because the distance depends upon the time that you've traveled, let's say, for this case. So the dependent variable goes on the side. Now, the points are obviously important, right? Let's first of all talk about that. So this point right here, that seems to be right on the y-axis here, or the distance marker axis, this represents 0 time and a distance. So at the very start of whenever we started measuring this, this situation, the person or the object was at 5 meters, is the unit here, at 0 minutes. So when we started timing, the person or the object was 5 meters away from some reference point, okay, at the 5 meter mark. Now, in 1 minute, this object started at 5 meters and it went to 11 meters, okay? So it changed 6 meters in 1 minute. So you have a second position. You also have the slope of this line, that is the change in the vertical quantity divided by the change in the horizontal quantity gives you also a slope or a rate of change. Does that sound familiar? Rate of change or a slope? We talked about slope before? Do you guys know about slope? Yeah. Yes? Y, okay, this is a y-intercept. Yeah, slope is slope between 2 points on a graph. The slope of the line connecting those 2 points would be the ratio of the change in the y, the vertical variable, the vertical quantity, divided by the change in the horizontal quantity between 2 points. Okay, I'll talk more about slope as we go through. But this is a rate of change. So in 1 minute, this person, let's say, walked 6 meters or crawled 6 meters or whatever. So the rate of change was 6 meters per 1 minute. Does that make sense? Yeah. All right. So now this line right here, okay, represents a decrease in distance away from some point. They go from 11 down to 7 meters. You see that? 11 meters down to 7 meters. And it took them a little bit longer time, from 1 minute to actually to 3 minutes. So this is a very steep increase in distance. This is a less steep, but it's a decrease. You see? And so the steepness of the line also gives you some information about how the rate of change is. A very steep line is a sharp rate of change, is a high rate of change. A flat line or a very small slope line, like just a barely above or below horizontal, is a small rate of change, okay? So at this flat point, notice that between 3 minutes and 5 minutes, the person, I'm going to just say it's a person, this person did not change position. So the person stood there for 2 minutes and did not change position. That's what it looks like, okay? Then they walked 1 meter in 1 minute. It's really slow. Maybe this is like an ant or something. I don't know, like an ant crawling. 1 meter in 1 minute. And then we have, from 8 down to 4. So that's a negative 4 meter change, right? Down 4 meters in 1 minute. And then a moderate decrease here. This is 4 meters in change from 4 down to 0 in 7 to 14 in 7 minutes. Okay, so 4 meters per 7 minutes. So the object or the person is moving quite fast in the steep parts. It's moving quite slow in the flat or not so steep parts. The flat is like not moving. That make sense? Understando?
Yep, understanding.
Okay. All right, let's look at this one. So here's another graph. And here we have a title for this one, A Scuba Diver's Dive. Okay. So that gives us some information about what the depth of what, the time. So this is a person that's diving. And notice that, you know, this shape of the graph is not necessarily a picture of the situation, right? The scuba diver does not climb up and then climb up some more like a mountain or something. No. This is representing depth. So sometimes you have to be careful about what the graph looks like and what the graph means. So you can kind of see that at 0 depth, this is like the water level, right? At 0 depth. So the scuba diver goes to a 12-meter depth in a span of 4 minutes. So I'm going to start to write some things down here on this. So the depth goes from 0 to 12, so that's a negative 12-meter change. Okay, from 0 down to 12, it's depth, remember, in 4 minutes. All right, so that rate of change, the slope of this line, is negative 3 meters per minute. As an average, if you go 12 meters in 4 minutes down, then you're averaging 3 meters for every 1 minute. Does that make sense? 3, 6, 9, 12. Yeah? Easy? This is, okay. Some of you are sleeping or praying over there. Can you lift up your heads? Thank you. If you're praying for my instruction, I appreciate that. Yeah. Hi. Wake time now. Yeah. Okay, good. Thank you. Okay, so what's happening in this section of the graph? Nothing. Well, what do you mean by nothing?
No movement.
No change in, no movement, okay? No change in depth. So the scuba diver has dived down, okay? We don't know how far laterally they go. It doesn't say. This doesn't say. It just says water depth. So they could have like been swimming this way like this for 4 minutes and then down to 12. And then they could be swimming side to side, but they're not changing depth. So to say that nothing is happening because it's flat, not necessarily. It just means that over this time period, there's been no change in depth. Okay, so we'll be a little more exact. So it could be that the scuba diver has found some kind of like coral shelf or something, and so they've gone down here, and now they're exploring the coral reef and the fishes and all that sort of stuff, right? Okay. Then what happens? They're tired of this little shelf here, then they're going to go deeper to a 20-meter depth. And then they're going to explore down at the 20-meter depth for a while. Does that make sense? No. Okay. So what's happening in this part of the graph here? Okay. So the depth is decreasing, which means that the scuba diver is actually coming back up to the surface. Does the scuba diver stop on her way up? No. Maybe? Well, a stop would be a no change in position for a certain amount of time, but because this line is continuous, it's the same straightness, it doesn't have like a break. So if she's going to stop somewhere, there's going to be a little bit at least, right? And then she could maybe go to the surface a little slower, right? That could be like a stop. I'll use red. Or she could be like coming back to the surface really quickly and then stopping. And then really quickly, very steep, and then stopping again. And then just like taking her time on the surface, and then coming to the surface, right? So there's lots of different information you can communicate in a graph. But yeah, this person is just returning to the surface. At what rate? Let's determine the rate here. So how do I determine the rate that this person is returning to the surface? 12? Okay, is it 12 minutes? Okay, what is this? What minute is this?
14.
Oh, it's 14, right. So 14 to 24, this is 26, 28, this is 30. You see how each of these are 2? Each of these are 2. So 14 to 30 is 16 minutes, right? 16 minutes, okay. And what is the rate of, what's the depth change? The person has gone up 20 meters. Why? Because they started at 20 and went down to 0. So even though it looks like it's going down, it's depth. So they're going up 20 meters in, what do we say, 16 minutes? 16 minutes. And so that becomes, can I simplify this at all, like as a fraction? What is that as a fraction? I can divide by 2. That's 10 over 8. I can divide that by 2. That's 5 over 4. So 5 over 4 meters per minute. What's that as a decimal? 1.25 meters per minute. Okay? So lots of times in word problems, decimals are totally fine. I mentioned the other day that I want you to be learning how to work with fractions because that's going to be very important moving forward in math, because some of you are not comfortable with working in fractions. So try to think about simplifying fractions as well, but it certainly would be more appropriate as a decimal in a lot of like actual word problems. Okay? So that's 1.25 meters per minute. Okay? Kind of going pretty slow, right? But okay. Okay, any other thoughts or questions about this graph? There could be a lot going on that we don't know about, but what we do know about is time and depth that the diver goes. All right. Let's do example 1 from the textbook here. So this is a bit large. I'm going to try and get it all on one screen for you. Each point on this graph represents a bag of popping corn. Explain the answer to each question below. So the title is Cost and Masses of Various Bags of Popcorn. So if you have a bag that is, what does this B represent? It looks like it's about 500. Yeah, I would say about 500. Because this is 600 right here. So this is about halfway between 4 and 6. So that's about 500. Good. So 500 grams costs about $2. You see that? So 500 grams right here, that's where that goes to, costs $2. That's where that goes to. Yes? Makes sense? Which is good. So which bag is the most expensive? Which bag is the most expensive total amount of money? Yeah, the one that's, I guess, the dot that's higher, right, than all the other ones. How much does it cost? Are each of these 1? 1, 2, 3, 4, 5, 6, 7. No, you're right, first time. It's over here at 7. Yeah. So C, and it's $7. Okay? Which bag has the least mass? The least mass, yeah, the smallest bag is the smallest number. B, what's its mass? We already talked about that. 500 grams. Which bags have the same mass? Ah, very good. D and E, because they have the same mass, which is this mass right here. So D, comma, E. Which bags cost the same? Are there any that cost the same? Very good. Cost would be this axis here. So there's A and E cost the exact same. Okay? A and E. Which bag, C or D, has the better value for money? So the better value for money, how do we find that?
It's E, because A is the same price.
It's C or D. C or D. Now, this is where you might have to just do some calculations. You might have to do some calculations, right? So C, what? Siri is talking to me. Oh, C or D. See? Stupid phones. So C or D. All right. So C costs more, but weighs less. You see that? C costs more, but weighs less. So you don't even have to do any calculations. You can kind of see here, right? Which is the better value for money? Well, D, you pay less, but you get more. So definitely D. Do you see that? So we could actually figure it out. Let's just be sure. 7 for 1,600. So Okay, watch this. If you want to know the price per gram, make sure you divide the price per grams. Okay, if you want to know the cost per gram or the cost, make sure the money's on top. Okay, so what's 7 divided by 1,600? What's that? Who's got it? 0.04375. 0.04375. Okay. What is that's the C. So D, this is C. D is, this looks like what? 550? 550 divided by 1,800 grams. So what's that one? 0.003?
Yeah, 305.
Oh, yeah. 30, okay, that's fine. Okay, so we asked which was the better value. You see how D costs less per gram? This is per gram. So it's a really small number, but you have $0.003 per gram, and here's $0.004 per gram. So this D is a better value. Yeah. Okay. Now, if I asked you which is a better value and how do you know, then this is what you'd have to do. You'd have to show me some numbers here to compare. Okay? How's everybody feeling about this? 5 out of 5? Understand? 5 out of 5? What? 4, 3, 2, 1? You don't get it? Where are we at? Okay. Okay. So is it always the dependent variable divided by the independent variable? If you're finding slope, it is. It's always this. That's the change in this one divided by the change in this one. If you're finding slope. If you're finding value for money, so like which costs the lowest money, then you're going to want to do money divided by grams and see which one's the smallest. When would you do grams divided by money? Well, if you wanted to say, you know, what are the grams per dollar? Then you would do grams divided by dollars, and that's how many grams you could get for $1 if you wanted to do that. All right, last example. So let's sketch a graph for a given situation, or situatio, apparently I have on my screen here. So sketch a graph for a given situatio. All right, Samuel went on a bicycle ride. He accelerated until he reached a speed of 20 kilometers per hour. Then he cycled for 30 minutes at approximately 20 kilometers per hour. Okay, well, first of all, what are my variables on my graph here?
Speed time.
So speed and time. Now, remember, time is passing, right? So you can't control the time that's passing. That is independent of whatever else we're doing, so that's going to go on the bottom. Yeah, I'm going to get this on the same screen. Okay. So what does he do here? He accelerates until he reaches a speed of 20 kilometers per hour. So let's put 20 around here somewhere. 20. So he goes until he gets 20 kilometers per hour. Now, does it say how long it took him to get here?
30 minutes.
Well, it doesn't say how long it took him to get to 20, though. He then cycled for 30 minutes at this speed. So we do know from here to here is 30 minutes, right? Sorry. I know that this is 30 minutes in between. Okay. He arrived at the bottom of the hill and his speed decreased to approximately 5 kilometers an hour for 10 minutes. So, he arrived at the bottom of the hill and his speed decreased to approximately 5. So we got to go down to 5. For 10 minutes as he cycled up the hill. So he's another
This is confusing.
This actually is a little confusing, yeah. Samuel arrived at the bottom of the hill. So this is the bottom of the hill after the 30 minutes of this, right? He's going down the hill pretty fast. His speed then decreased to approximately 5 kilometers per hour for another 10 minutes. So from here to here is 10. And he cycled up the hill. He stopped at the top of the hill for 10 minutes. So what's his speed when he stopped?
0.
So he goes down to 0 for 10 minutes, I guess.
Okay.
Yeah. He stopped at the top of the hill for 10 minutes. So I don't know how long it takes him to, if he's like instantly stopped. So it's pretty instant, I would say, going from this 5 kilometers an hour down to 0. So it's like another 10 minutes there. But yeah, he almost changed his speed instantaneously, I guess. All right, well, that's a bit of a tough one. But you guys get this, though? Like, this is a very steep, it's not vertical. You guys get that? Okay. Yeah. So it doesn't say how long it took him to change speeds, but if we can assume that, yeah, these would be pretty steep here, here, and here. Be pretty steep. Okay. Yeah, actually, I don't like that question. Sketch a graph of the speed as a function of time. Label each section of the graph and explain what it represents. Okay. This section, A. Shh. Guys, keep focus, please. We're almost done. This section, A, is him accelerating from a stop, accelerating to 20 kilometers per hour. B is him staying at 20 kilometers an hour for 30 minutes. C is him C is him changing from 20 down to 5 kilometers. D is him keeping a constant speed of 5 kilometers for 10 minutes as he cycles up the hill. And then E is him stopping at the top of the hill briefly, and then F would be him remaining stopped at the top of the hill. So something like that. Does that make sense? Okay. All right. If you want to check your textbook along with that, you can. All right. So I've covered pretty much everything that you're going to see inside your in your homework assignment there for this section. So you have about 10 minutes to work on your assignment, which I'll pop up on the screen here in a second.